Good afternoon. My name is Judah Ginsburg, and I'm happy to welcome you all to what promises to be a very exciting session on cold fusion 20 years later. This briefing is coming to you from the 237th National Meeting of the American Chemical Society in Salt Lake City. In a few minutes, I'll ask each of our speakers to identify himself or herself, give us their institutional affiliation, and a brief, no more than 5-minute summary of your research. And then we will go to questions both from the audience that's here in this briefing room and online. But before we do so, a few ground rules, if you will. As I've indicated, in addition to the reporters in this room, others are watching online and can ask questions as well. And they're joining us through our Ustream channel. I would ask all journalists to please give your name and institutional affiliation when you ask a question. ACS science writers may join in the questions, but we'll defer to news media who are present and watching online as well. For those of you who are joining us here, I ask that you please use the microphone that will be provided when you ask a question. So raise your hand, I'll call on you, and the microphone will magically appear. For news media and bloggers online, we encourage you to embed or link to our videos. An archive of this video will be available on our Ustream page as soon as this briefing is over. So let's move straight ahead and begin, and I'd like to call on Jan Marwin to begin. Would you please, sir?
Right, so I make the start. My name is Jan Marwin. I'm a German citizen. I'm my affiliation here. I'm running my own research laboratory that's called Marwin Chemie in Berlin, Adlershof. I established this laboratory when I came back from Canada and found sponsors to support my ideas. I'm a trained electrochemist. My specialization and expertise lies in the electrochemical deposition and properties of nanostructured materials such as palladium. And in this way I have a long year expertise in sorting out the hydrogen region of nanostructured palladium, and I found out some very interesting and I think for this fight, LENR fight, significant issues. Do you want me something to say now about this symposium, right?
Please.
All right, okay. Yes, I'm the organizer of this symposium that's called New Energy Technology. Now here taking place in Salt Lake City, and it's I'm at the start 2 years ago. I was in Chicago. There we had there was a beginning. We had a half-day session, invited speakers talking about the LENR research. I was very happy about this start. It was also a very good press release, and we also published in the process of organizing these symposiums a book that's called Low Energy Nuclear Reactions, ACS, Oxford University Press, contains 16 papers giving strong experimental evidence for LENR, LENR, historical name as cold fusion, and also giving some indications about the theoretical model that exists in this field. So half a year ago I had the second turn to organize a symposium in Philadelphia at the ACS. There we had a full-day session, and now in Salt Lake City we have a 3-day session. So you see on this that's a growing thing. So now Salt Lake City, it is a, well, let me say, the birthplace of this scientific controversy. It's because of the Fleischmann-Pons experiment 20 years ago, the idea to induce nuclear reactions at room temperature when penetrating, when deuterium or hydrogen penetrates into the bulk material lattice, and so the nuclear reactions can be enhanced at room temperature. So this was the idea. Yes, and on the basis of this, the LENR research is been here presented in Salt Lake City. Right. Yes, the attention why I'm organizing, the aim why I'm organizing the symposium is because I want to contribute to the idea to include low energy nuclear reaction into mainstream science. This is, I think, a significant issue, as mainstream science over many years mostly ignored low energy nuclear reactions. This is a pity because for one reason, through my experience, through my experiments in Southampton, where I did my PhD, in Montreal, where I did my postdoc, and now in Berlin, in my research laboratory, I found out very much truth in this topic, LENR, and evidence. And also in the process of dealing with other people's research on LENR, I found also very, very good indication and evidence that this might work. So I think in terms of confronting the climate change and finding a suitable, adequate alternative energy sources, I think there is now ignorance wouldn't help us. So I think skepticism to select the garbage from the wheat, to select the truth from fantasy in science is fine. We all need this. But the significant issue now is to turn into this and, well, to focus on this issue. And the ideal case would be that at chemistry physics departments at the universities worldwide, that they start to build up some research groups on this, because there is any delay is very detrimental to this, and it would not help us. So, right, this is I wanted to say.
Thank you very much. Steve Krivit, please.
Thank you, Judah. I'm not a scientist. I'm a journalist.
Give your affiliation, please.
Steve Krivit, editor of NewEnergyTimes.com. Also, I've had the privilege to work with Jan Marwan as a co-editor of the American Chemical Society Low Energy Nuclear Reaction Sourcebook. The first volume was published August last year. We're working on the second volume. I'm also involved in some other publications as well. I've been following this field for 8 years, and it's been a very interesting journey so far. My interest right now is to provide a brief overview for particularly people who have not been following the field closely, or perhaps not at all, for the last 20 years. So just briefly, the experimental work is probably what has driven the success of the field so far, which has provided for the longevity of this field. It was predicted that this would die, that this field would die within weeks, within months of its announcement at the University of Utah. It hasn't. Far from it. The experimental evidence is probably what has been supporting it. You'll hear some more of that from some of the other presenters here. What's not strong are the theoretical aspects of the work, and this has been, from day one, continuing through right now, an extremely frustrating and controversial aspect of the research. Now, we're here at the Chemical Society. Chemists have a tendency to be a little bit more forgiving than physicists when you propose that a mechanism at room temperature and room pressure is producing fusion processes. I found that the physicists are not so open-minded. There's some brilliant people who have worked on developing theoretical models to explain this as fusion processes. Very brilliant, very creative people. I do not know to the extent that their models are correct. I don't know what the status is on those models. It's been very, very difficult to get those hypotheses supported with broad acceptance. Some people have accused the field of wishful thinking, and it's unfortunate because the experimental evidence is, at least in my opinion after 8 years, unambiguous. Dr. Moss will speak about some neutrons perhaps that were reported earlier today that are just absolutely very rigorous. So the theoretical expectations are extremely challenging. However, there is another theory that is not reported here today that hypothesizes that this is not fusion, that this is based on a weak interaction process. It's a very interesting hypothesis and suggestion, and it could explain a broad variety of what has been observed with deuterium, with hydrogen, with light water, with heavy water. Could explain some of the extremely unusual transmutations. So, will we know the answer to any of this theoretical stuff soon? I doubt it. Probably will take many years. I hope it doesn't take more decades. And I would say there's one question I always get asked. Is cold fusion real? So I answer this with 3 answers. 1, it's really 3 questions. Is the science real? Well, experimentally, empirically, absolutely, I would say that the science is real. Is it really a fusion process? I don't know. 3, is it a solution to the energy problem? Is it a practical source of energy? That too, I don't know yet. But everything else I know, from what I've seen, there's still that possibility, and it's still observed to be clean and without harmful radiation.
Thank you very much. Dr. Danino, would you please give us your full name, institutional affiliation, and a few remarks? Thank you.
Hi, my name is Antonella Danino, and I came from Italy. I work to Enea, it's near Rome, and I've been working on cold fusion since 1989.
Can you speak a little louder?
Louder,
yeah.
Yes. I've been involved in research on cold fusion since 1989, and I've been working on it for 15 years. Now I changed my fields of investigation because I had to quit these fields because of the problem to find funds for these fields. It's quite a pity. But this gave me the opportunity to look at this field from a different point of view. So I can consider several things that I missed when I was too busy in my lab. So what we did in Frascati was to do an experiment which aim was to prove the nuclear nature of the excess heat measured during electrolytic experiment. And to do this, we designed a special apparatus able to detect very tiny amount of helium-4 that is supposed to be the main nuclear ash of the phenomena. And we did it. We tried to publish the data 5 years ago, more or less, but we didn't succeed in it. So what happens later? I think that now we have a very, in some way, a scattered picture of low energy nuclear reaction in condensed matter. There are several very convincing experimental evidence, and there are also several theoretical approach. But it's very difficult to get to a unique picture of the field. This is also because it's very difficult to work in a regular way. There is no place for this research in university, so it's very difficult to involve young people on it. And the average, the mean age of the participant to this field is very high. This is not good for science. So I think it could be very useful for science to make some more efforts in this field.
Dr. Boss, please.
Hello, I'm Pamela Boss. I'm at SPAWAR Systems Center Pacific. Our group has actually presented 3 presentations describing the results we have obtained over the past 20 years. Initial criticism of the purported palladium-deuterium low-energy nuclear reactors centered upon the phenomena's irreproducibility. Many years later, this was understood to be due to the long incubation times required to fully load the palladium with deuterium. However, early on, Dr. Stanislav Shpak, an electrochemist at the Naval Laboratory in San Diego, developed an alternative method of initiating low-energy nuclear reactions using palladium-deuterium co-deposition. In this process, palladium metal is plated out in the presence of deuterium gas. The advantage of this approach are that the palladium metal loads instantly with deuterium, the experiments can be done faster, there is a great deal of experimental flexibility, and the experiments are reproducible. Other groups from SRI, UCSD, Texas A&M, the Navy Laboratory in China Lake, and Berkeley have obtained positive results using the co-deposition process. Early experiments using thermocouples showed that the co-deposition electrode was always hotter than the solution. This indicated that the electrode was the heat source and not Joule heating. Calorimetric measurements done by Dr. Melvin Miles of China Lake showed that the rates of excess enthalpy generation using electrodes prepared by the co-deposition technique were comparable to that obtained when palladium bulk electrodes were used. Infrared imaging of electrodes prepared by co-deposition in collaboration with Professor Simnad of UCSD and Dr. Todd Evans of General Atomics showed that the presence of hotspots were indicative of mini explosions. This was confirmed in an experiment suggested by Dr. Lowell Wood of Lawrence Livermore National Laboratory by co-depositing palladium and deuterium on a transducer that recorded the mini explosive pressure and heat transients as they occurred. Ultimately, We concluded that heat alone was not going to convince others that nuclear reactions were occurring inside the palladium lattice. Our focus changed to look for evidence of nuclear ash. Using conventional nuclear diagnostics, we showed that the emission of X-rays, gamma rays, and tritium occurred as a result of co-deposition. These emissions occurred sporadically and in bursts. To enhance these effects, experiments were conducted in the presence of either an external electric or magnetic field. Examination of the palladium deposits at the end of the experiment showed significant morphological changes that were consistent with the localized melting of the metal. Further analysis of these molten-like features showed the presence of new elements such as aluminum, magnesium, calcium, silicon, and zinc. More recent experiments using a solid-state nuclear track edge detector during co-deposition have shown the emission of both charged particles and neutrons. The observed size distribution of the particles and neutrons obtained as a result of co-deposition is consistent with those observed for DD and DT fusion. Taking all the data together, we have compelling evidence that nuclear reactions are stimulated by electrochemical processes. To date, these observations have been published in 20 peer-reviewed journal papers and 1 peer-reviewed symposium book. 2 additional papers have been accepted for publication later this year. As to the future, there are a number of potential uses for the heat and nuclear emissions generated as a result of the low-energy nuclear reactions occurring inside a metal lattice. Heat can be directly converted into power without the emission of greenhouse gases. The energetic particles can be directly converted into electricity, as is done in radioisotope thermoelectric generators. Uses of neutrons include the remediation of radioactive waste and the production of radioisotopes used in medical, industrial, and environmental applications. However, in order to achieve its full potential, additional research is needed to determine the mechanism by which low-energy nuclear reactions occur within a metal lattice. Only then will it be possible to optimize and control these reactions for a given application. Thank you.
Pass the mic down, please. Dr. Dash, would you please give us your name, institutional affiliation, and a 5-minute summary with you?
I'm John Dash.
Speak a little louder, sir.
I'm John Dash, and I'm Professor Emeritus at Portland State University in Portland, Oregon. In 1989, a few weeks after Pons and Fleischmann announced fusion in a bottle, my department had asked me to look into this. So I read the Fleischmann-Pons paper, and it seemed interesting. So with the help of a graduate student, we put together an experiment, not exactly the way F&P did, but we cobbled whatever we had around the school, and we only had a tiny piece of palladium, and we squeezed it until it was large enough to make an electrode. So we turned the power on, and to my amazement, the palladium foils start to curl. Wow, what's going on here? I'd done a lot of electron deposition experiments, and I never saw anything like that. So anyway, then my specialty is electron microscopy. So I went to the scanning electron microscope and saw craters on the surface. And so I've been convinced that there's something going on very dramatic. This is 20 years later, and when I started out, I had all brown hair. Okay, so I think that that's the problem with the field, is that the gray hairs are adding up, and we're getting slower, and we need to get the younger generation involved. So starting in 1989, I've been training high school apprentices for 2 months during the summer. So I've trained 40 kids so far, and 7 master's degree theses and 2 doctoral dissertations were written at my school, and these have to pass muster of examining faculty or they don't get the degree. So they all passed muster, and all except one had positive results. So what I've specialized in is microscopy, and that includes the morphology and the composition. And you can get the composition down at the 1 micron level, 1 cubic micron. So it's a very powerful tool. And what we found early on is the appearance of localized concentrations of unexpected elements. So others have found helium, a possible nuclear ash, and we've found, in the case of palladium, we find silver as a nuclear ash, and in the case of titanium, vanadium, chromium, iron. So that's where I keep that's where my expertise is. We keep working on that, and also measuring excess heat. And I think we have to make an effort to train the younger generation, because I believe this field, which is in its infancy, has a long way to go.
Thank you, Dr. Dash. Dr. Srinivasan.
Thank you very much, Dr. Ginsberg. Oh, it's two.
That's fine.
Well, as I said, my name is Mahadev Srinivasan. I used to work for the Baba Atomic Research Center in Bombay. BARC, as it is called, is the largest nuclear research laboratory in India, which is engaged in all aspects of developing nuclear technology. We got involved in this field almost on day one, and thanks to a small newspaper report on the 24th of March 1989, there was a little report, 4-line statement, which said that Pons and Fleischmann, in a press conference conducted right here in Salt Lake City, had found a very simple way to produce nuclear fusion reactions in a so-called battery and bottle experiment, and that it emitted neutrons. That was what got me interested. I was the head of the neutron physics division at that point in time, and I said, well, if a little bottle can produce neutrons, it is fantastic. So we got around, and I should specifically pay credit to the director of the Baba Atomic Research Center at that point in time, Dr. P.K. Iyengar, who later became chairman of the Indian Atomic Energy Commission. He was a very open-minded physicist, and so he really encouraged us. He did something very interesting. He invited people from many divisions of BARC. As I said, BARC has about 50 divisions, so people from different divisions with different backgrounds, and he encouraged us to set up experiments using whatever equipment you have to verify this. Is it really true that neutrons are being produced in a little battery and bottle experiment? So that was what got us all going. In a sense, it was healthy competition between many different divisions. This morning, I briefly reviewed the paper we presented. I had the opportunity to present the results of the first year's work right here in Salt Lake City, March 28th of 1990, when the first ICCF-1 was conducted here. And I don't want to give you all the details, but except that 12 different groups using different approaches, we all found evidence for the production of neutrons and tritium. The nuclear origin of the phenomenon was very clearly evident. Now, unfortunately, Dr. Iyengar was the then director, got promoted to the chairman's position, and the next person who took over, he was also a physicist, but he had a slightly different perspective, and he was perhaps guided by what is happening in the US. At that point in time, the US Department of Energy, as you know, convened this committee And it is extremely unfortunate that this committee set up by DOE said cold fusion was all nonsense. That one phenomenon has had a very unhealthy effect on this. But those of us who are involved have continued. There are several hundred people all over the world, 7 or 8 or 9 countries working on it. Over the last 20 years, the evidence is absolutely convincing. And I must admit, when we started in this business, we were just looking for a fusion reaction in one particular cell, the palladium D2O cell. But what has happened is truly astonishing. The phenomenon seems to be something very, very fundamental. This is truly a revolution in nuclear science that is underway. It is extremely pity that the mainstream scientific community, I'm reminded of the old story of Galileo, who called the priests and said, please look into the telescope, look at the moons of Jupiter or whatever it is. And the people refuse. It is very sad that mainstream community people have decided cold fusion is nonsense, period. I will not look at it. My theory tells me it cannot work. So that is the very unfortunate, but the results over the last 20 years, I congratulate Jean Marwan and Steve Krivit in organizing these meetings. There have been 14 international conferences so far. Every year or every 1.5 years, the people come together. Wonderful work. And I can just, before closing down, there seem to be true, shall we say, 2 branches to the scientific research that's going on. One group of people are looking for excess heat, anomalous heat production accompanied by helium. That path is likely to lead to a small tabletop device which can produce energy. But what is more interesting to me is the observations which have come up. It was not there in 1989, but in the last decade or two, as Dr. John Dosh mentioned, people have found evidence for the occurrence of nuclear transmutation reactions. Now, I should place it in perspective for the chemist. As you all know, according to textbook physics, textbook chemistry, no matter what you do, you cannot convert one element to another. Lavoisier said that in 1700 and whatever it is. But we find in simple tabletop experiment, new elements are being created. Something very, very interesting is going on. And another very interesting thing is that this research is very inexpensive. People, ideal for, it gives you an opportunity to revive the good old days of small science, rather than going for simple experiments done by Pam Boss and others show the richness of scientific data you can find in a little inexpensive tabletop experiment. So my only appeal to whoever is listening, please take the trouble. All these results are published, and there's a very single website, www.lenr.org, where all the papers published are available. And it is fascinating science. Students can do it. As John Dosh has said, it is an excellent opportunity to participate in a revolution that is going on. If only people would take the trouble to look at it. Thank you.
Well, thank you all for your presentations. And now we will. Thank you. Now we will entertain questions. Please wait for the microphone after you're called upon. Give us your name and institutional affiliation, and please indicate to whom you are intending your question.
Hello, my name is Mitch Garcia. I'm at the Chemistry Blog. I was just kind of curious, why heat? If you're having a nuclear reaction, you should be having gamma rays coming out. Why are you looking just for heat?
Who are you? Just to whom?
Everyone in the audience in general.
Anyone?
Well, let me put it this way. There's one possible reaction which could be D plus D going to helium. Although it has not been proven. Helium is observed, it's measured, it's a fact. It is a fact that heat-producing cells in many groups have found helium. And quantity of helium produced, if you correlate it with the amount of excess heat produced, it appears to be leading to an amount of about 24 MeV.
Yes.
But the question is still open.
I have these calculations just right here.
Yeah.
I did the real trick. So D plus P to make helium will give off a 5.5 mega electron volt gamma ray. Why are you looking for heat and not this gamma ray?
Steve Krivit.
I think Steve Krivit wants to say something.
Hi, Mitch. I'm glad you showed up this year. You said you were going to show up last meeting, but we missed you. One thing I'd like to point out is That's Srinivasan, and there's a couple of other people here. One misunderstanding that's happened is that perhaps there's some people here, but there are several hundred other people, and who represent quite a collection of breadth and depth of works. So I don't know if it's necessarily fair to expect him to be a spokesperson for the people who are doing research on heat and helium. I could recommend to you that you might follow that up with a gentleman named Michael McCubry at SRI International. You know, he would certainly be an expert on neutrons and tritium. And, you know, one of the reasons perhaps why there is not a great search, and perhaps Antonella can respond, perhaps there's not a great search for gamma is because it hasn't been seen early on. Do you want to add anything to that?
Hi, I'm Pam Boss. We actually did some measurements of X-rays and gamma rays, and what we found is that if things occur in bursts or in short duration and you're doing long acquisition times, you can average it away. So all you'll essentially see will be just an increase in the count rate, not necessarily determine where the excess occurred.
I think we have a question online.
That's right. We've got a question from Mark Anderson of IEE Spectrum. Question for Dr. Mosier Boss. Your group published an LENR paper in the January 2009 issue of the German journal.
Nature Wissenschaft.
What is it? Yeah. Could you please briefly describe in layman's terms what you found in that paper?
Okay, what we found in our co-deposition experiments in the presence of heavy water was the presence of something called triple tracks. Triple tracks in the CR39 are the result of a reaction in which the carbon atom shatters, and you can see it in a three-pronged star where the three alpha particles are breaking away from a center point. We calculated the energies of the neutrons that cause these triple tracks. They're on the order of 12 to 15 MeV, and such neutron energies are consistent with DT fusion.
Anybody else in front of me want to comment? Any other questions? Yes.
I have more of a historical question here, and that is, it's been 20 years.
Can you identify yourself, please?
Oh, I'm sorry. I'm Ed Yates with KSL Television. We're the NBC affiliate in Salt Lake City. You've had 20 years of evolution here, and somebody on the panel mentioned that there is this pressing need to get mainstream science interested in whatever process this is, whether it be called cold fusion or something else. I mean, 20 years evolution, how do you make that move now? There still seems to be this cold fusion club, which is a group of scientists that continue experimenting, but when does it move beyond that and you convince mainstream science that there's something to this?
Isn't American Chemical Society mainstream science?
Yes, it is. But other than the American Chemical Society, you've got your enemies out there, the physicists. So
the physicists are coming to this a bit slowly. They have the researchers from what I've seen. They're trying their hardest to get this through the normal scientific channels, through the journals. And it's working. Nature Wissenschaft, European Journal of Applied Physics, Japanese Journal of Applied Physics. It's working. You haven't seen it in Nature, you haven't seen it in Science yet. You haven't seen it so much in the United States physics journals. But, you know, it's been 20 years of controversy. It may take a little time, but it's working. That's where it's going.
To this question, I want to make a short point. I think that, well, if you compare the amount, the number of people working in cold fusion or LENR over the last 20 years, and if you compare this number to the number of people working in hot fusion science or even fuel cells, whatever, this is not a comparison. This is a big difference. And so, taking this, we have to come to the conclusion that those scientists dealing with LENR over the last 20 years made a lot, big progress, but there are not many. It requires much more people, and therefore it would be really good to include this into mainstream science, and so to approach this idea to all the scientists. This is in principle the message I want to come across with, to address this to all the scientists and to get young people into this project. I mean, we cannot expect the cold fusion scientists to solve the problem of this world. This is 100, 200 people. This is not possible. We need much more. And if you consider this, if you compare this to the number of people working in hot fusion, well, I mean, I don't need to answer to this question now. But this is my comment.
Aaron Rowe in the back.
Aaron Rowe from the Wired Science blog. So, taken as a whole, it seems like you're lacking important evidence that low-energy nuclear reactions are taking place, and you're lacking a theoretical framework for why it's taking place. And you're concerned that the scientific community, as the mainstream scientific community, doesn't take you seriously. Is it possibly premature to be holding a press conference right now?
I could do it.
Okay, Steve?
Aaron, if I think I heard the first part of your question, I think you said that there seems to be lacking experimental evidence?
No, lacking important experimental evidence, as if you have some pieces of a puzzle and there are some very, very big pieces missing. So if this was a puzzle of a ship, you would have a mast and nothing else.
If you knew that you were looking for a ship. If you knew you were looking for a ship. They don't know what they're looking for. This is exploratory science. If you think you're looking for fusion, then yes, your analogy works. If you take away that assumption and expect that you're looking for the unexpected, that analogy doesn't work. You have to go back to your fundamental science. Experiment, control. Effect, stimulus and effect. It gets one more point. It gets very, very simple. If you look at the research, you see a signal with an experiment, you see a signal with a control. The signal could be heat, it could be helium, it could be neutron. There is a ton of experimental evidence. So I don't know what it means, but I do know that it's anomalous and unexplained, at least for the last few hundred years.
So I guess what I was getting at is that it seems like you're very concerned with being taken seriously, and yet this press conference seems to be a repeat of the Pons and Fleischmann announcement in the sense that it's...
Why do you say that? I don't understand.
Because you haven't established either a theoretical framework or or some important experimental evidence like the gamma releases that should be taking place. So,
did you go to the session this morning?
No.
Then how would you know what the experimental evidence is?
Well, I'm mostly addressing the question that Mitch asked, which is that there should be, so we have a nuclear chemist here saying that there should be, if fusion is taking place, gamma releases, and that you haven't been able to measure those.
Yeah, good. And Mitch is right. He's got a good point. We have two different areas of the research, the experimental to the theoretical, and that's what I said in my introduction. Experimental work is very solid. The theoretical work, who knows, but I'll turn it over to someone else.
I'm sorry, I don't think I understood the question very clearly, but you seem to be harping on the point that there is not enough gamma rays. Is that it? People have not. Now, this is, I think, one of the fundamental problems. The problem is you are assuming that a nuclear reaction, if it occurs, has to be accompanied by gamma rays. What if there's a new mechanism by which a nuclear reaction inside a solid can continue to be a nuclear reaction, but the gamma ray is suppressed by certain condensed matter nuclear effects? I think it's fair to say by now enough people have made measurements of the excess heat, and one thing is clear: the absence of intense amount of gamma rays has been established. Okay, a small amount of gammas may be coming out of the cell, you are still trying to tag onto it. I think that is one of the beautiful things about the Fleischmann-Pons effect from day one. People used to call it the not dead graduate student effect. Simple calculations shows if you are producing 1 watt of excess heat, you should have got so many neutrons, so many gamma rays, and that was enough to kill the graduate student. That has not occurred. That is one of the beautiful things about the Fleischmann-Pons effect. But the theory has still not come up. It is very clear. Even neutrons, we did measure neutrons, we did measure tritium. None of these things are commensurate with the amount of excess heat produced. I think the only thing that has been established which is more or less commensurate is neutral helium, non-radioactive helium. I think that is fair to say that has been established, but what is the mechanism which produces helium is still an open question. But are nuclear products being produced? Yes, people have measured charged particles, people have measured this thing, but that is not the main reaction which is responsible for the so-called excess heat. I hope I have made my
So what should be the main
question is not clear.
Go ahead, Alan.
what should be the main scientific takeaways from what's been accomplished in low energy nuclear reactions in the last 2 years?
Anybody in particular?
What was the question? Main?
No, I didn't get the question.
We are not able to hear you. Sorry. You can speak up properly.
What should be the major takeaways from recently announced low energy nuclear reaction research? Basically, what should be the major takeaways from this?
Do you want me to say anything?
Boss.
Pardon?
It would be great if you could address the question.
Okay, what was the question again, please?
The question is, what are the newest takeaway messages from your research?
Well, our more recent research has shown that there are energetic particles, are consistent with energetic particles and neutrons being emitted during the co-deposition process. What's really nice about the CR39 detectors are that it's an integrating detector, so we don't have to worry about the sporadic burst-like nature of the phenomenon, as has been shown to be the case with using electronic measuring devices. You know, it's been challenging, but we have been able to get our papers published in mainstream journals.
Can I answer that?
Yeah. Okay.
Can I add something to the last question? So what is important to underline is that this is not new exotic physics. This is the usual solid old physics, but it is applied in a different context. So nuclear physics, as we know, the fusion physics, is applied usually in very dilute plasmas. They are the plasma used in hot fusion, in thermonuclear fusion. In this case, we have a very different scenario that is condensed matter. So it's not a new physics, it's just a new scenario with the old rules, of course. So this is very important to be understood. It's nothing exceptional. So old physics, a new way to apply it. What we know now, after 20 years, is that there are very solid evidence, experimental evidence, and there is also a theory that has to be applied inside condensed matter. Cold fusion is not an oddity of the nature. It was not a nightmare made out by Martin Fleischmann 20 years ago, but it steps out from a deep knowledge of several phenomena already known in condensed matter since 30s, because people forget to study physics. What has been done in 30s, in 20s, is still real, is still valid in physics. So we understand a lot. We can learn a lot studying physics. So this is not an oddity. Now it could be very time-consuming now to do all the path, but it is possible. We have published several papers, and they are available in literature, in which you can see that there is a way, a very long way of a different way to apply physics in condensed matter. That it is. This is the novelty of this field of research.
Thank you very much. And Dr. Srinivasan, further comment?
Well, you asked a question about the takeaway. What was the, although this group is not present at this meeting, one of the very important results which were presented, which have come out in the last 1 or 2 years, is the work of Professor Arata at the University of Osaka. He has come up with a very simple, not electrolysis, a simple device where he starts with a nano powder of palladium in a zirconia matrix, lets in deuterium gas, and it produces heat. You can't even use the word excess heat, because the word excess heat is applicable when you put in a certain amount of energy and get out a certain amount of energy or power. In his experiment, he just started with a cold device. He introduces the deuterium, and the nanoparticles of palladium seem to be producing the phenomenon. He has measured helium once again. So his experiments, he has found several watts of power running for months and weeks. that is a direction in which a number of people are jumping into from the point of device application. This is what I call the heat producing, helium generating approach. Similarly, the work at SRA International by Mike McCoubrey and the energetics technologies of Israel, and I think they have work done. The reproducibly, one of the questions which arose 20 years ago was, your devices are not reproducible. Work over the last 20 years has demonstrated, people have learned that you have to. But your original question, the mystery remains. It is not. One thing is absolutely clear. You cannot judge this phenomenon using the standards of, shall we say, hot fusion. It is a nuclear reaction, which is a different reaction. In the condensed matter, something seems to be happening. That is where the richness of this whole phenomenon comes in. And as I said, the experiments are so simple. One doesn't need a large investment to get into it. So we appeal to the scientific community to jump in and investigate the phenomenon.
Steve has a quick comment.
I'll try to make it quick. Aaron, I want to go back to your question. You know, in a sense, it's a very good question, because you're sitting there and you're looking for the news and information about this subject matter, and you're not hearing about it. You're expecting to read about it in the conventional science journals, and you're not hearing about it. So you don't know, and it's not your fault. So to get back to your question, isn't this a repeat? It's not a fair question, because they've done the work, they've published the papers in the journals, they're here at a science conference presenting science, and this press conference is coming after that. Please come to the rest of the session that starts at 1:30.
Question over here.
Yes, I'm Scott Traub. I'm the technical editor of Infinite Energy magazine. Now, you mentioned that you wanted to make this part of mainstream science, and obviously you're here at the American Chemical Society for that reason. But some of you must be getting funding, and we have different people from different countries. I'd like some comments about that. The level of funding, what's going on. That has not, to my knowledge, that's not widely known. And also patent issues. I understand there aren't patents being issued in this subject in this country, but they are being issued elsewhere. Thank you. I am.
Well, actually, Scott, we do have a patent. We obtained a patent on a beryllium coating on the palladium, which did improve the loading characteristics of the palladium.
Yes, but in most situations they've been blocked. Right? That's my understanding.
We have another patent that's going through the process right now with regards to the energetic particles. And Melvin Miles, of course, and Imam have a patent on the palladium boron system.
But this is relatively new development.
Well, my original beryllium patent came out in the early 90s.
Okay. I'd like comments from Steve.
Anybody else?
The situation for science in Italy is not so it's very bad, of course. We had very hard time in this period. Generally for science, in particular for cold fusion or low energy nuclear science. But this is a very general problem. About patent, we do not have a patent about the way to produce heat, but we try to have a patent about the method we invented to measure helium-4, because it was a very complicated measurement. So we try to have patent of pieces of the method we used, and the method was a very, very good acceptance by the scientific community. The method, not the measure, the method, at the point that now it is required from colleagues for hot fusion. They ask us to provide them our instrument in order to measure the helium-3 produced during the hot fusion reaction. So the method will be validated by our colleagues of hot fusion. The same colleague that they don't want to see inside the telescope, the Galilean telescope.
Any other comments?
Scott, you want me to answer that?
Yes.
I think you're a plant. You knew the answer to that question.
Well, I'm an editor of Infinite Energy magazine.
Okay, my answer, from what I can tell, from what I hear, The patents that go in with the words cold fusion in it, they get challenged because people say it doesn't look like thermonuclear fusion, and they get yanked out. The patents that go in and say, hey, we're seeing heat, we're seeing this phenomenological effects, they get a little further in the process.
Do you think that this is becoming a national security issue?
I can't confirm or deny that.
Steve, question, please take the microphone and identify yourself.
Mike Taggett with Henry Works down in El Paso. And Steve, probably you can address this. Is the DOE going to lighten up a little bit under this administration and start looking at this kind of research a little more favorably?
If you'll permit me to just pass along some rumors, I'm sorry, but this information doesn't come to me with very hard evidence. But in the last few weeks, I've been hearing that people are submitting proposals to DOE, DOD, and EPA. As you can imagine, they're probably not thrilled to have the exposure about this subject because it still does carry a significant stigma. But it seems that people are they're seeing the papers. You know, their group's paper published a few months ago. That's having an effect. But there have been secret meetings. I went to one of them in San Diego in 2007. DTRA, Defense Threat Reduction Agency, has been interested in this for several years. There have been several DTRA meetings. Some of the people in this room have been to those meetings and have spoken at those meetings. So DTRA, DOE in general, it seems like there are pockets that are interested, but with the new administration, perhaps there's a little bit more interest in non-oil alternatives.
Anybody else? Any other questions? Did you want to comment?
Our first patent application was in 1990, and the title said low temperature nuclear fusion. And I've been battling the patent office ever since then, including, what's he doing? Including trying to get the Supreme Court to hear it, and they turned it down. Anyway, there seems to be no end in sight. They send us a no, and we send them a nasty reply, and it just goes on forever. So I think they're hoping that I'll die soon.
Any other questions? A question online.
We've got a question from Bo Varga of nanotechnologynow.com. What is the best net energy output to date?
And who is that intended for?
I think it's not directed to anybody.
Is there any takers on this? I can do it. Steve? Yeah. The question is, what's the best net energy output?
That's right.
A few years ago, there was a group based in Califon, New Jersey, with a laboratory in Omer, Israel, named Energetics Technologies. I don't know if they've been able to repeat this, but a few years ago they had a 2,500% experiment, 2,500% excess heat experiment. Also, shortly after that, they repeated it and had a 1,600% excess heat. That strong result hasn't been repeated as far as I know. However, they were involved with a replication effort that included researchers from SRI International, Enea Frascati, that showed a high reproducibility of the excess heat effect, ranging from 10% to 100%. A few watts, I think, were the highest of that group.
Thanks.
Any other questions?
Mike Woods from the ACS Science Writing Unit. For anyone on the panel, do the results vary with the source of the palladium?
John?
And if so, why?
As far as I know, the preparation of the palladium is all important. Typically, if I have a piece of palladium and I snip off a part, and run an experiment, say using half of my snippings in one cell and the other half in another cell, chances are I don't get the same result. And so there's a mystery. As Srini mentioned, Arata is using nanoparticles, people that use the bulk palladium, say a few millimeters diameter for their electrodes, they have to wait weeks for something to happen. And if you use thin foils or nanoparticles, things happen pretty fast. So I think that the answer to your question is it does vary a lot. We stay to the same source time after time, and we still have a lot of variability.
Online question?
That's right. This is another question from Mark Anderson of IEEE Spectrum. What is the best published and replicated excess heat result? What's the citation?
What's that?
Yeah, in our book. It's a Leonard Source book.
The Arata paper, okay. No, I don't know the publication exactly, but it's ICCF 14, he had a paper in the 14th International Conference. Excellent paper, but all their work is published in the Japanese journal JJ Applied Physics. It's also available online from the LENR website. You can download it. So the reproducibility is certainly improving with time, and people have learned how to improve it, how to process the material. But the tendency now is to go in for nanoparticles and thinner foils and so on.
Thank you.
Yeah. To answer this question, I mean, shortly, I can only recommend people to read this book, Low Energy Nuclear Reaction Source Book. It's a ACS Oxford University Press. It's the principal, it's a peer review book, not a principal, it's a peer review book, and any significant results, or also on excess heat, they're published there. This is all written there. So I only can recommend people to buy this book. ACS will be very happy about this, and to read it.
Any other questions? Well, if not, I want to thank our panel. I'm sorry, we do have one more online.
One quick one from Bo Varga again. What is the optimal nanoparticle size?
You remember that?
What is the optimal nanoparticle size?
No, but the one that was used by Arata, I think 4 nanometers, was it? 4 to 10 or something like that. You remember the particles used by Arata's experiment? I think somewhere in the 4 to 10 nanometer range.
Yeah, sounds right.
In zirconia matrix.
Thanks.
Okay, I want to thank all of our members. Thank you very much for participating. It was very, very interesting. Thank you all for attending. And let me remind, please, our online audience that the next press briefing will be at 3 p.m. Mountain Time. That's 5 o'clock Eastern Time. See you then.
Thank you.